Hello everyone and welcome to lecture number 9 for this course on nonlinear optimization. Today we will talk about conjugate gradient method, specifically the Fletcher-Reeves method from the book of Fletcher. We will go there slowly, starting from very basic ideas and motivation, and then quickly try to understand how and why this method works. So the idea behind these conjugate gradient methods is to have a quick, cheap method which tries to exploit some second order information about the function, but without explicitly computing the Hessian of the function. So in some sense it is like the quasi-Newton methods that we studied earlier, but these methods are slightly different in the sense that the directions specified in this method satisfy certain nice properties called conjugacy. So we'll start with this idea of conjugate directions. Before that, we will quickly discuss an even simpler idea called linear independence. So I think most of you would be familiar with what is linear independence. It just means that given a set of vectors, let's say x1 to xk, all from Rn, they are linearly independent if we cannot write any one of them as a linear combination of others. If none of them is a linear combination of others. More precisely, consider alpha 1 x1 plus alpha 2 x2 plus alpha k xk equal to 0, where alpha 1 to alpha k are constants or are in R1, then the only possible solution is alpha 1 equal to alpha 2 equal to alpha k equal to 0. You can verify yourself very easily using this definition that 1 0 1 0 1 1 and let's say 3 3 0 are linearly independent. On the other hand, 1 0 1 0 1 1 and 3 minus 2 1 are not, because I can write 3 minus 2 1 equal to let's say 3 times 101 minus 2 times 0 1 1, and that means I have found these alpha values so that their linear combination is 0 and alphas are non-zero. So and geometrically in 2 dimensions, these 2 vectors are linearly independent, but these 2 vectors are not. It is also possible to show that in n dimensions you can pick at most n linearly independent directions, and this topic we will come back to very soon again when we start talking about linear optimization. So linear independence means that by scaling and adding other vectors in the set, I will not be able to get my current vector. This is useful in search procedures, because if you pick a direction which is linearly independent of the previously selected directions, that means you are potentially going or exploring a region which you could not possibly have done with the earlier directions just by changing the alpha values or the step lengths. Related to this idea of linear independence is orthogonality, which also most of you should be familiar. S1, S2 vectors are orthogonal or perpendicular to each other if S1 transpose S2 is equal to 0, and geometrically what it means is S1 and S2 make a 90-degree angle. Okay, what you can I'm sorry about this number, this doesn't really mean anything. So what you can easily prove is if S1, S2, S3, Sk are mutually orthogonal pairwise, that means if you pick any two and take the product, it comes out to 0. Then S1, S2, Sk are also linearly independent. And this is somewhat easy to prove. You can possibly do it in your assignment. The converse is not true. Okay. Linear independence doesn't mean that the vectors are actually orthogonal to each other. Okay. And the previous example of linearly independent vectors that we wrote are really not orthogonal to each other. So one idea when we are searching for a minimum is to search in linearly independent direction, so that you intuitively you feel that you are trying to look in areas which you potentially could not have explored in the previous iterations. And that means you also cover a lot of new ground while exploring things. It also leads to some good theoretical properties, especially when you are solving for simple functions like a quadratic function. Okay, so we will start applying this conjugate gradient method to quadratic functions. So we will consider a quadratic function f is equal to half x transpose gx plus b transpose x, maybe, plus some constant, with g positive definite. Recall that g positive definite means x transpose gx is always greater than 0 whenever x is non-zero. Of course, when x is 0, then x transpose gx is 0. So if I was only minimizing the first term, x transpose gx, then clearly by definition this minimum has to be 0 when x is 0, because for all other x's I have some positive number. When we also have a linear term in addition to this quadratic, then we can just apply the first order test and get the optimal point, which is x star equal to minus g inverse times b. And it's easy to see that it's going to be a unique optimal solution to this problem. So this problem is very easy to find the answer. You just have to invert g and multiply it with b. You can also solve the system of equation gx star equal to b minus b to get the value of x star. So this conjugate gradient method can be motivated by trying to solve this rather very simple problem whose solution we already know of. But what conjugate gradient method does avoids computing G inverse. So that means it's very different from Newton methods. It also avoids any approximations of G or G inverse. So it is different from quasi-Newton methods also. The method merely chooses search directions slightly different from the steepest descent. Okay, so we know that steepest descent is a good method. It leads to global convergence, but is sometimes slow. So conjugate gradient tries to improve upon the steepest descent by picking the steepest descent direction and then modifying the direction slightly. So Sk is equal to minus of Gk plus something something. Okay, so this correction term actually gives a slightly better method. So before listing the steps of the method, we should try to understand what is this meaning of conjugate gradients. So definition. And this is section 2.4 from Fletcher's book. A set of non-zero vectors. So none of the vectors in this set can be zero, as let's take n. We can take, let's take n just to be consistent with the book. So this set is said to be conjugate to a positive definite matrix G, again size n cross n. So these two n's are same. If so when do we say they are the set is conjugate? If S1 or Si times Sj, and this has to be transpose, equal to 0 for all ij, I not equal to j. So that means S1 transpose G S2 equal to S1 equal to 0. Same with S2 transpose G S3 and so on and so forth. Okay, so you take any two vectors from this set different from each other and look at this product with G, it should come out to 0. What it means is Si is orthogonal or perpendicular to GSJ. So GSJ is a vector just like S. It is of size n cross 1. So recall that orthogonality means Si times Sj is 0. So here we are not insisting on they being orthogonal to each other. We are saying that they sort of become orthogonal once I multiply some of them by G. Okay, but not both. Alright. So I'm not multiplying Si by G, I'm just multiplying Sj by G. I could also multiply Si by G and not multiply Sj by anything. So really, what we are saying is that under the influence of this matrix G, these vectors become orthogonal to each other. So when we multiply a vector by a matrix, we are either scaling or rotating it. You can try to see some examples in 2 dimensions. What happens when we multiply any vector by a positive definite matrix. So what we are saying that after that scaling and rotation, this vector should become orthogonal to Si. And recollect that G is the Hessian of the quadratic. So we are essentially trying to look at directions which are orthogonal to each other under the influence of the Hessian of the objective. Okay, and that may help us to sort of have good step lengths and not zigzag too much like we were doing in steepest descent. So recall the example of steepest descent being slow when the contours are elongated. So by taking these conjugate directions, we are trying to avoid that zigzagging. Now now let us look at some nice properties of these conjugacy, which will motivate us to develop a general purpose method. So this is